first came on this plant, pretty frightening with the size and the noise. And when you first go into the job, you think I'll never learn it. But you get used to it. Some of my friends work in the factories, they say, oh, we produced so many shirts yesterday. Oh, we got a free shirt from work yesterday. Well, you can't turn around and say, I got a free bucket of ammonia. You just don't get anything like that.
But if you're in an ammonia plant, you don't want to see the stuff. The whole object of the exercise is to keep it inside the pipes, inside the tanks, and away down to the storage. One of the questions that we must consider as manufacturers is how to contain this stuff in the pots and pans in such a way that it doesn't harm the folk who work there, and just as importantly, it doesn't harm the people who live in Billingham or Middlesbrough.
I think the size of the plants would attract anybody. The complexity, this fascinated me when I first arrived. I just couldn't get over the size of the plant. It took me several months to appreciate exactly what happened inside the plant. I would like to put across to anybody who came around a plant like this that it's not really as technically complicated as it may first seem. But basically, it's all a very simple, organized process. Organizing people, organizing materials, and the way of doing things.
A chemical plant isn't like most factories. It doesn't make shirts, cars, clocks or fridges. Instead, it manufactures the stuff that finished products are made of. Oil, coal, natural gas and other raw materials are used by a chemical plant and turned into other kinds of stuff. Sulfuric acid maybe, ammonia and ethylene. These substances often aren't a great deal of use in themselves, but other factories buy them to use as their raw materials. A factory will need other materials too, metals, rubber, wood and perhaps paper. All these things are manufactured into the useful products that people want to buy. So, a chemical plant takes raw materials and turns them into the chemical intermediates that other factories need to make useful products. In this programme, we'll be looking in detail at just one of those chemicals, ammonia. Ammonia is the starting point for many different things. It helps in making dyestuffs and man-made fibres such as nylon. Ammonia is used to make nitric acid, and that's used in the manufacture of high explosives. But this is the most important use of all, ammonia to make fertilizers. In the 20th century, we've come to depend on chemical fertilizers, millions of tons every year. NH3, the formula is simple enough. Let's see if it's as simple to make. Ammonia is nitrogen combined with hydrogen. We'll start on a very modest scale. We'll try to combine just small quantities of the two gases. This is nitrogen being bubbled into an upside-down test tube. The liquid is a dilute acid containing a chemical indicator. Any ammonia we make will neutralize the acid and cause the indicator to change color. Next, we add 3 times the volume of hydrogen. And now we'll try to combine the two gases to make ammonia. Between the two metal electrodes at the top, we apply a very high electrical voltage. You can see a spark if we dim the lights. And around the spark there should be a high enough temperature to make the two gases combine. But it's a slow process, so we'll see the film speeded up about 100 times. Look for a darkening of the test liquid. That will mean ammonia. It's slow because, unfortunately, the spark also splits ammonia up. the process will certainly have to be much faster to be of any use on a larger scale. And how can we alter things so we don't need to stop after one batch and start all over again? Well, here's one way. And how to solve the problem that the spark also breaks ammonia up. The answer here is to use a catalyst instead. In the real process, this is a special mixture prepared mainly from iron, which speeds up the chemical reaction enormously. When ammonia is made on an industrial scale, hundreds of tons of catalyst are used in a single plant. But the catalyst is no good when it's cold, so the next improvement is to add a heater. And the reaction is improved again if the gases are fed in at a high pressure. So, add a pump. The real compressor is big and powerful, as much power in fact as 4 diesel locomotives. The tower on the left is the heater. The one on the right is the reactor where the ammonia is actually made. Several times a day, samples of the ammonia product are taken for laboratory analysis. When the ammonia is made, it's at a high temperature, and it's a gas. But here you can see it's been liquefied. In fact, liquid ammonia is extremely cold. You can see the flask frosting up. So to collect and store the ammonia as a liquid, an essential part of the plant is a cooler. By causing the ammonia gas to liquefy, the cooler also has the effect of separating the ammonia from any unreacted nitrogen and hydrogen. Both these unreacted gases would need a much lower temperature for them to liquefy as well. Notice that in this design, we're just wasting these unreacted gases. So take them back to the start of the process and feed them in again. And now, in a simplified form, that's the heart of the real ammonia process. The tower that actually makes the ammonia is only one small part of the whole plant. Most of the plant is designed to provide the nitrogen and hydrogen needed to start with. This is done by processing raw materials. North Sea gas is one of the raw materials. It's very rich in hydrogen. The gas is taken right onto the chemical plant by pipeline. What happens is this. The natural gas is reacted with steam to give the hydrogen and also carbon dioxide, which can be removed later. This reaction takes place in an important section of the plant called the primary reformer. The primary reformer is a large shed-like building. On the inside, it's a furnace. If you look through an inspection window, you can see vertical pipes glowing red hot. Packed inside the pipes, another catalyst to help the steam and natural gas react together. So now the hydrogen needed has been prepared. What about the nitrogen? To get this, some of the hydrogen just made is burnt with air. Air, in fact, is one of the major raw materials for making ammonia. Air is burnt with hydrogen to give nitrogen and water. Coming out at the right now is a mixture of 4 gases. A device called a separator removes the 2 that aren't needed. The carbon dioxide extracted is useful for other industries and is sold. The separator isn't just one unit, but several. The two towers to the left are where the carbon dioxide is removed. Now the story is almost complete. On the right, there are now just the two gases needed to make ammonia. So, hydrogen and nitrogen are made from natural gas, air and steam. And with careful planning, the proportions of the gases are the correct ones for making ammonia, 3 parts hydrogen to 1 part nitrogen. All we have to do now is add the ammonia-making section and join them up. And this really is the complete system, a simplified picture of what happens in the real plant. Very little on the plant goes to waste. Steam is raised using excess heat from the chemical reactions. The steam is used to run compressors and generators, and also as a chemical to react with the North Sea gas. Everything is designed very carefully to make the best possible use of energy and raw materials. It takes days just to get a chemical plant started. So as far as possible, it's never allowed to stop. Night and day, it's watched and cared for, almost as though it were alive.
It's a very dynamic plant. You've got to be on your toes all the time, and you've got to be willing to work unusual hours. I would say most of us have been called out many nights during the year. It's simply because the plant doesn't recognize normal day hours. You know, you have to follow hours that are going to suit the plant. There's always something going on these 3 plants, and sometimes we wish it would be quieter.
Number 2 unit, syngas compressor, trouble alarm.
Every job you do readings and check things. You walk around looking for leaks, listening for things. With the readings, you're taking pressures, temperatures. You're looking for anything out of the ordinary. The only instrument we carry is a pencil. And maybe it's a wheel key, which you just use for operating the stiff valves and what have you. You have to clean up the catwalks on some of the jobs. But if there's anything goes wrong, we're outside all the time. You know, getting soaking wet in the rain and that. Gets a little bit depressing sometimes, you know. But it's got to be done. You've got to put it right.
This is where the whole plant is controlled. Every valve, every pump, every turbine and generator. This is where the state of health of every part of the vast machine is watched and recorded. The temperatures, the gas flows, the pressures. Everything is designed with one thought in mind above all others. The plant must be safe. And if it ever gets unsafe, it must be shut down.
Well, these plants are covered with safety devices or safeguards. If a plant gets into a dangerous condition, that particular piece of plant will trip. If you can visualize a single stream ammonia plant as the old domino line, if you flick one, the rest in that direction will fall down. If you've lost the front end of this plant, the complete plant would trip all the way down. Most of it is automatic. It will either trip or be tripped by the control operators.
Number 2 unit, syngas compressor operator.
You run for a period of time when all 3 plants run quite steady, and then you hit a patch where you get a couple of plants tripping out due to faults. And you run for a period of time where you have a real hectic period, and then life will settle down again when the plants will start to run pretty well continual again.
Can you put more out? This might be the shift manager now. Yeah. Are you Chris? Are we trying to lift this CO2 main for you now? Jimmy will get the boys out.
Put another 2,000 out on the CO2 main.
Well, it's a very close team relationship, and we'll go out as a group on our days off. And once every couple of months we have a night out, a good nosh, and we'll get together. It keeps the team together.
We've got a problem, Chris, on these 127Cs out here. To do something about it.
How many leaks are there?
Well, we can't tell really. Could be about 4 on the bottom pass, the third pass, and about 12 on the bad one. Pretty heavily, you can't really really see. Anyway, the metallurgists reckon it's high temperature. The slack band coatings come off, and the temperature's got at it, and we're going to have to choose, I think, between doing an online repair or swapping the buggers over.
John, we can solve this job quite easily. The vessel is completely symmetrical, and we could turn the one around over the other.
Yeah.
So that the hot one would therefore be in the cold region.
Yeah, yeah.
Therefore, the damaged part would be in the cooler side of the gas stream.
Yeah, I'm not sure how relevant this business is at the cold side.
The problem to be solved is typical of those that come to light during routine inspection. Very bad corrosion has been discovered on the inside of a gas cooler unit. Action has to be taken without delay.
To protect it, obviously we couldn't paint the tubes themselves, but it would give us a little bit more time. It's much quicker, of course.
Yeah. Well, look, you're going to vessels now?
Yes.
Well, are you going to be around this evening?
Well, I'll be at home, but I'll be available if I'm needed.
Yeah.
Quite often we have major vessel faults, defects in welds, and all the vessels on the plant are examined periodically, and when we do examine them, we frequently find faults which we've got to put right, and quite often these are major repairs.
The pipe being lifted out is the corroded gas cooler unit. The next step will be to fit a temporary replacement.
The job is very interesting because it's so varied. One day you can be inside a brick-lined reformer, repairing a failed riser tube that normally runs at 900 degrees C. This is a 5-day repair job. The next day you can be involved in the stripping down of a compressor that runs at 10,000 revs per minute, compresses ammonia to 140 atmospheres. The following day you can be involved in a very simple problem, a small piping problem. But there's a tremendous variation. It's very interesting.
Well, I was always interested in chemistry when I was at school. Yeah, that's what I went in the labs for at first. You know, you tended to be washing up beakers and test tubes all the time. This you're more involved with it than you are in a lab, I think. Being on a chemical plant, you can see how the reactions take place all the time. You can see natural, well, you can't actually see it, but you know there's natural gas going in one end and ammonia coming out the other. It's amazing, really, when you think about it.
It is amazing. On this plant, every day, 1,000 tons of ammonia are made out of North Sea gas, water, and plain thin air. More than half a ton of ammonia every minute, and most of it goes to make fertilizer. Nothing could seem more different from the open countryside than this plumber's paradise of chemical technology. Yet it's a curious thought that our agriculture depends on it.